Okay, so we'll do one quick example of how to compute different parts of an EDTA titration curve in the presence of an auxiliary complexing agent or another ligand, in this case ammonia. So the example we have is that you're titrating about a millimolar of zinc ion with a millimolar concentration EDTA fixed at pH 10 with a buffer, but you do that in the presence of 0.1 molar ammonia. And the reason is that at elevated pHs, zinc is known to form strong complexes with hydroxide and precipitate out of solution. So first thing that we need to do is find the fraction of zinc 2 plus that's not bound to ammonia. So that's going to be the alpha zinc. So zinc forms four stable complexes with ammonia. So you could have, we don't really need to know these, but you could have zinc plus 1 ammonia. You could have zinc plus 2 ammonias, plus 3 ammonias, and plus 4 ammonias. And those are all the possible zinc ammonia equilibria, which means that when we're computing the alpha fraction, we need to consider the equilibria for all of those. So we're going to use the cumulative formation constant for each, so that's beta 1, 2, 3, 4. So you can look these up either on the internet. These come straight from an appendix in the back of your book. So I'm not going to write them all out here just because it's a lot of writing, but you can grab these straight from the back of the book. So that's what I'm using to compute these. And then remember, these were all multiplied by the ligand concentration. The ligand concentration here is 0.1. So we'll input 0.1 for each of the ammonia concentrations, and then that'll allow us to solve for the fraction of zinc 2 plus in the solution. So that gives us about 1.8 times 10 to the minus 5. Oops, that's not molar. That's just the fraction. So the fraction of zinc, remember the fraction is really the concentration of zinc unbound free zinc over total zinc, total being derived from this inclusion of all four of those different equilibria with zinc. So that means that roughly 2 100,000ths are 2 out of 100,000 zinc ions are unbound inside the solution. So a small fraction of that is present. Second thing we need to do then is determine at pH 10, which is where we're working with this solution, what fraction of Y4 minus is unbound. And so that would be the alpha Y4 minus, which we're accustomed to using. That comes straight out of your textbook, just in that table. So we've used this value before. So at pH 10, the fraction is 0.30. And then finally, we need to know the formation constant for zinc, for this, zinc plus the Y4 minus compound to make the zinc Y2 minus. So that Kf just comes straight from your textbook again. That log Kf of this is pretty large, 16.5. So the Kf then is 10 to the 16.5. So last step here then is to modify our Kf for the fractions of zinc that are actually present and the fractions of Y4 minus that are actually present in the system, considering that this Kf is referring to those two species. So we're going to modify each of those species into the equilibrium formation constant by computing the sort of double conditional, which would then be the alpha zinc times the alpha Y4 minus times the original Kf. And that gives us a value of 1.7 times 10 to the 11. So just so that we're clear, we're comparing, we just modified our Kf because only a small fraction of zinc and a small fraction of Y4 minus are present. So essentially the effective concentrations of both of those are quite a bit lower than what they would be at different pHs, or if we were considering all four complexations of the ammonia. So under good circumstances, under ideal circumstances where the alphas are 1, where all of that species exists in solution, then we would have had a Kf of 10 to the 16.5, this huge number. But when we modify those for lower concentrations because they're fractionally present, that dropped our coefficient down to a factor of 11. So that dropped us 5.5 orders of magnitude. This is still heavily product favored, but we just dropped it down by a factor of like 100,000, which will change then the equilibrium concentration of zinc in the solution at any given point in the titration curve. So let's start well before the equivalence point. So we'd already determined the equivalence point's at 50 mils. I just gave you that, but you could have easily computed that with M1V1. So I saved that step. And so our first point on the titration curve is just 20 mils, so we're well before that. So we can, we'll just do this pretty quickly then and just say, well, the concentration of zinc 2 plus is going to be in excess because we're far before we've added the stoichiometric equivalent of EDTA. So we're in excess zinc land, and we're just going to think about, well, what fraction of zinc is left by thinking about the fraction along the way to equivalence. If equivalence is at 50, we've added 20. That means 50 minus 20 is the fraction left, 30 out of 50. That would be our sort of fractional amount of zinc left in the system that we haven't complexed, times whatever the original concentration was, which was 1.00 times 10 to the minus 3 molar. That's coming straight off of the list here. And then the dilution factor here. So we had originally 50 mils of this stuff, and now we have 70 mils of this stuff. So we've done this several times, so I'm not going to walk you through each of the steps, but generically this makes sense. And that gives us a value of 4.3 times 10 to the minus 4 molar in excess. But remember, so far, this computation has only considered the impacts of EDTA, and really saying that EDTA binds 1-to-1. That's where this 20 comes from, is it just assumes that all of the 20 mils of EDTA that were added, those remove the zinc from the system. But it has not considered the fact that this also is in the presence of this other auxiliary complexing agent, ammonia, which is our second step and is the new step added to the system that you haven't done. So now we just need to multiply our original zinc concentration. I'll write that as zinc after EDTA. I'll just write EDTA here. That's this value. So the concentration after we've added 20 mils of EDTA will go in here, and then we need to multiply that by the fraction of zinc in the system based on the equilibria with the complexing agent ammonia. And so in this case, that fraction, which I deleted, but is 1.8 times 10 to the minus 5. So I'll rewrite that. Zinc is 1.8 times 10 to the minus 5. So that value gets inserted here. So that allows us to compute the new zinc free. Remember, what we're computing here is the zinc concentration unbound to EDTA or ammonia. So that gives me a value of 7.7 times 10 to the minus 9 molar, which if you take the negative log of that, the P zinc here is 8.11. So we could drop this curve. I'm not going to, just because it's not super important to do that at the moment. But remember, the whole impetus in doing it this way, the reason why you've got all this high background level of ammonia in the system to start with is because of the presence of oxides that typically form when you do these titrations. Okay, so the second point is at equivalence, and that's 50 mils. So remember, at equivalence, what you've done is added exactly enough of the Y4 minus to completely complex all the stoichiometric amount of zinc in the system. So what you have at that moment is everything complex in the form of the zinc Y2 minus. But then, of course, if that's what you have in water, added to water, it's going to trickle back a little bit based on whatever that formation constant is in the system, or 1 over that. And so we need to know, in order to sort of compensate for this in like an I or E or ice plot, we need to know what is the concentration of zinc Y2 minus. And as we did in previous EDTA titrations, the concentration is equal to whatever the formal concentration of the zinc was that we added to the system, which is the 1 millimolar coming from up here, except we've now added 50 mils to the original 50 mils. So to compute our zinc Y2 minus naught, which is our formal concentration before it's allowed to proceed, that's going to be the 1.00 times 10 to the minus 3 molar times our original volume, which was 50 mils, divided by the 100 mils, which is the 50 plus 50. That will give us a nominal formal concentration of 5.00 times 10 to the minus 4 molar. And that's what we're going to start with then. Here is 5.00 times 10 to the minus 4, and some amount of that's going to trickle backward, starting with 0 of each of these. So this will be 5.00 times 10 to the minus 4 minus x at equilibrium, and then we'll have some x of zinc and the Y4 minus that get liberated based on the Kf value. Okay, so now we just need to draft this up into an equilibrium expression that we're used to. So, but in this case, we're using our K double prime F here because really what we're wondering is the extent to which this equilibrium will occur even in the presence of ammonia. So that is significantly lower than what it would have occurred if there were no ammonia in the system. So what we end up with is K double prime F equal to concentration of the complex zinc Y2 minus divided by zinc 2 plus times concentration of Y4 minus here, which in this case is 5 times 10 to the minus 4 minus x, there should be a minus x here, over x squared. Is equal to 1.7 times 10 to the minus 11. So just like I did before, this is the Kf going in the back would be going the reverse direction would be 1 over Kf would be 1 over 10 to the 11, which would be a really tiny number. So I'm going to assume this is 0. You don't have to. You could solve this with the quadratic. I'll assume this is 0, and when I do that, I get an x value which is the same as the zinc concentration here, equal to 5.4 times 10 to the minus 8 molar. And that's not all. So that told me what the zinc concentration would be in the presence of ammonia and EDTA with our adjusted constant, but it actually doesn't tell me what fraction of that zinc is free or unbound. And so for that last step, so this is really just considering zinc and only EDTA, even though we consider the double prime here, that just told us how much would trickle back in just the presence of this equilibrium. Now we would need to then take to figure out what the actual zinc 2 plus free concentration is. That's going to be equal to the zinc 2 plus that we just computed, only considering the EDTA, multiplied by that fractional factor here, or alpha zinc, which was the 1.8 times 10 to the minus 5. And so if we take this value and pop it in here, and we take this alpha value and we pop it in here, we compute the actual free concentration, which is 9.7 times 10 to the minus 13 molar, which if we take the negative log of that, that gives us a P zinc of 12.01. So quite low concentrations, 10 to the minus 12.0. Okay, so last step is then just post-equivalence point. So here we're talking 10 mils past at 60. And remember when we did this in the regular EDTA titration, what we're doing is just setting up the same equilibrium expression, but we're adjusting the concentrations of those species for the dilution factor, since we just added a bunch of EDTA to the original 50 mil volume. So that equilibrium expression looks like this. So this is the normal complex over the metal times the EDTA concentration. And that's equal to our formation constant times the fraction in the y4 minus form. The key here, which makes it a little confusing, is that in this case, we know this to be just the normal conditional formation constant instead of the double prime. And in fact, we don't need to use the double prime because we don't need to consider ammonia for this last step. We don't need to consider ammonia anywhere post-equivalence. So no NH3 needed. The reason for this why not to include ammonia in post-equivalence computations is that because we are going to determine the concentration, the absolute concentration of zinc complex and EDTA, then we know those two values. We're not deducing it by an equilibrium that's dependent upon the fraction of zinc. Those two values are computed in absolute, and so this value is computed in absolute, and we do not need to consider the K double prime F in this case. So I'm probably not going to have you do anything quite too complex, at least in a closed book form, maybe in an open book form. But this does get a little bit confusing. But just know that because you're computing two variables that go into a defined ratio, then there's no need to consider what fraction of zinc because it's not part of the equilibrium itself. It's not, the ammonia is not a factor here. So to determine the concentration of the two highlighted species here, all we're doing is assuming that all of the zinc 2 plus has been complexed as Y4 minus and turned into Y2 minus. So we just need to know what the formal concentration of zinc 2 plus was in the solution, and then we need to multiply by whatever that dilution factor is. So and for EDTA, all we'll do is take whatever the excess is and divide by the new dilution factor, or the new volume. So to find out the diluted concentration of the complex here, it's going to be whatever the formal concentration of zinc was, which was a millimolar, times whatever the original volume of the solution was, which was 50 mils. That'd give us the number of moles of the complex divided by the new volume, in which case that's 60 plus our original 50, that's 110 milliliters. So we compute that, that gives us a value of 4.5 times 10 to the minus 4. Similarly, if we want to look at the EDTA concentration, that's just going to be whatever is in excess, which in this case is the 10 mils, because it's 60 minus 50, 50 being the equivalence volume. So we've got 10 extra beyond equivalence divided again by the total volume, here 110, multiplied by the original concentration of the EDTA, which was also a millimolar in this case. So that gives us a value of 9.1 times 10 to the minus 5 molar. So this value will be substituted in here, and then this value will be substituted in here, and we know KF, and we know the fraction in Y4 minus, which is 0.3, so we can rearrange this and solve for zinc 2 plus. And if we solve for zinc 2 plus, that gives us a value of 5.3 times 10 to the minus 16. Negative log of that gives us a value of 15.28. So this is a fairly cumbersome process, but the goal was for you to think more conceptually about what's going on here. So if we zoom out and we think back to the original challenge, why we needed to invoke using an auxiliary complexing agent to begin with, or an extra ligand, that's just because anytime you want to do an EDTA titration, you're always going to be doing it at elevated pH to ensure that your dominant species in solution is Y4 minus. The problem with that is at elevated pHs, many of the metals, especially transition metals on the periodic table, tend to form metal oxides that become solid and they precipitate out of solution. If they turn into solid, then the apparent concentration of that thing goes down, which means when you're titrating that metal, you're only titrating a small fraction. And you wouldn't know that. you could, if you knew the equilibrium constants for the hydroxide formations, you could just compensate that in your computation here. So if you're thinking about calculating it, it doesn't really matter. We wouldn't need to be able to do this just to be able to calculate it. It doesn't change the challenge of calculation. We would just compute an alpha value for zinc based on the hydroxide species rather than the ligand species. No big deal. But in practice, you can't do that because you don't really know always what species are going to precipitate as various hydroxides, and you may not know all of the relevant equilibrium parameters. In that case, practically, you just remedy that and you say it doesn't matter, I'm just going to nullify all hydroxide formation by adding in ammonia at a reasonable concentration. Then when I titrate my system, what I'm actually titrating is only zinc and the free zinc, and not any of the other stuff in the system. And so it's important to sort of remember here that we're calculating a bunch of stuff, but we're calculating that based on sort of already knowing the answer, right? And you don't always know this. That's the point. Like this part here, the 1.00 times 10 to the minus 3 zinc, you wouldn't know that in a titration. The whole point is you are trying to figure this out using the EDTA titration, knowing that it goes as a one-to-one stoichiometry. So the purpose of using ammonia in this case is to allow us to get to that point, because none of the zinc has been locked up in an insoluble product that we can't access with the EDTA. So it's important to differentiate the calculation part of things from the experimental, because from the calculation perspective, you're saying, well, it doesn't, I don't get it. Why wouldn't we just why do we do all of this? Well, in that case, we already know the answer, and so it's important to differentiate the two.